In the previous topics, we have gone through how to construct small device or relatively large or complex circuit designs with many examples. And in this topic, we will be introducing how to structure larger designs or how to organize your design project. So assume you're a new component designer and you finish a nice component design with good simulation result. Now, how to put that onto a mask layout? So first, you have to define your goal for designing for such a DOE or design of experiment. For example, you would like to extract a good model, or you would like to extract certain parameters of your models, or you would like to optimize your device designs. And secondly, you would put your reference structures as well as making the real DOE designs. For example, sweep over several parameters on this device. And lastly, you would like to put a series of design onto a mask layout so that it can be a big GDS files together with your teammates' designs to be submitted to the foundry for fabrication. How is this organized? Today, as a photonics designer, you're probably part of a big team. You work independently on your own projects, and then you design part of the chip, and finally, the team coordinated within themselves to assemble the mask layout. We are seeing some team already implemented this method themselves. There could be a leader of the design team who's going to instill good design practices in your team members and to organize the design project and assemble the final layout. So how to get there with such an organization, which makes a more efficient design flow and the tape out workflow. So the key best practices lies in first, there's a good folder structure where every design team member follow the same practice. Practically, we need a regeneration script which generate the new designs once the design team member finish their design, and the final stage, the design leader have to regenerate the design that is going to be submitted. And another practical thing we will require is the merge script, which merge or automatically merge all the designs onto a single mask layout. The other aspects that we find which could ease the coordination between the team members is the logical naming of the components that could incorporate, for example, the wavelength information, the key aspects of the device layout geometry such as length and width, and for example, the mode information, whether it's TE or TM, and so forth in the naming of the components. So that's apparent to the team leader and yourself too. So everybody is going to follow the common rules among the team members. So we are sure that we are doing the same thing, and the team leader will be confident to merge the design and submit to the fab as fast as possible. So concretely, how does a project structure look like within such an organization? So briefly, on the left side, this is the PDK part, which is made of the library components. As we mentioned in the trainings that we introduced how the PDK is organized with component layout and simulations briefly. And on the right side, the structure is actually composed of several DOE design, DOE1, DOE2, DOE3, each with its layout information, the simulation results, and the regeneration script, which generates the final GDS. And in between this regeneration script, which the team leader will be running to obtain the final GDS of each DOE design. And we will mention later that it will also generate information text file containing the layout size, which is used to instruct us how to move around the GDS blocks of each DOE relative to the other blocks. And finally, we have this mask merging script that we put into this training material to assemble the mask in a semi-automatic way. So let's first take a look at the components library. So for each designer, they're going to contribute their component design into the PDK. So already here, we need to implement good practice on how the PDK is going to be organized. For this topic, we have a separate training topic on PDK management. So at Luceda, we recommend a certain PDK organization structure that every team could follow in order to reach a good design organization and also to facilitate the entire PDK-based design workflow. So to briefly mention again, of course, if you're interested, you could look at our dedicated training topic on how to manage the PDK. But here we briefly introduce the organization of the PDK structure. Also in your training repository, you will find out that we have put a Silicon Fab or SciFab PDK library, which is comprised of SciFab, which contains everything in the PDK, basically. And then under the SciFab directory, there's a IPKISS directory where everything that is IPKISS related that is put into here. And you have to make this as the root of your Python path so that in your designs, the Python interpreter will look for the Python libraries under this folder. And under this folder, there's also a SciFab directory named after your library name, here the SciFab. And that's where import library names come from. Again, under the SciFab directory, there are two directories, one called components, which contains all the components of your PDK, and the other one's called technology, which contains all the tech keys that is specific to a certain technology and where we could implement the definitions of the tech keys, such as the layer settings, the GDS settings, and so forth, which is related to the foundry technology information. What is relevant here is this components directory, where as a designer, you can implement your device design into this components directory. And lastly, in the SciFab folder structure, there's also one at the same level of your IPKISS folder isLedit. So this is the settings forLedit, the tenor layout editing tool. But this is optional. If you're using the IPKISS EDA plusLedit functionalities, you will be required to implement settings here in this directory. So let's say our component design is ready. You have your perfect design and it's implemented into your PDK library. Then we are going to implement the design of experiments or DOE. Deriving from your library component, we will have several DOEs. For example, we have a DOE of MMI device, we have a DOE of a spiral, and we have DOE of direction coupler. And they are organized in separate folder structure. So first, what is the design of experiments? That is the planning, conducting, analyzing, and interpreting controlled tests to evaluate the factors that control the value of a parameter of a group of parameters. So here it's actually a design of experiments in which the design introduces conditions that directly affect the output. So several examples include if we change the length of the device, if we change the waveguide width of a device, or change the curvature of the waveguide, or change the length of the waveguide spiral, and then we will analyze the output and extract information that is important to our goal. Now, how to prepare for a DOE design? So first, we need to identify which factors to be tested, for example, which device specifications that we would like to see as outcome that is going to be affected by, for example, the layout change, the width, the length, and so forth. And then we need to identify the levels of those factors. And thirdly, the structure and layout of the experimental runs and the operating conditions. And of course, we need to change one variable at a time for each DOE. And of course, we would also want to perform some simulation in advance to help identify the parameters to be swept. And now here's a list of literature which helps you to actually prepare for DOE. Here is actually the example of DOE design of the splitter. So here we are putting the splitter into a splitter tree circuit. So in this DOE, one set we will be sweeping over the band length while keeping the band height fixed. So here you will see the GDS output of the MMI-based splitter with the output band length of 5 micron and also with 4 microns. The other DOE, we will be fixing the length of the band and we will be actually varying the band height. As of the implementation of the design into the project structure as we have introduced with the schematic previously, we will see that there will be a top-level design project which represents all the designs that is going to be put onto the mask layout for this tape-out run. Here we name it as tape-out 2020-08, and it's based on the SciFab technology. Under this folder, we will put directly the name of the user. Here it's our colleague Chiara. And under Chiara's project, there will be several directories. So some are for the DOE design folders, the designs, the splitter height sweep, and also the splitter length sweep, the DOE2. And for each DOE directory, there is the actual script to design your DOE. There's also a regenerate script. So the output of your design, the DOE designs, will be actually generated into this GDS to merge folder where it stores actually the output of the regenerate script. So just to look at the regeneration script a bit closer, the regeneration step will happen after each DOE design project is created. And the regeneration script is actually used to generate the GDS file as we see before, and also the layout size information, which is stored in a text-based file. So again, this regeneration script is actually a file that anyone can run to generate an updated version of your design. And it's always called regenerate.py. The output of this regeneration script is first a GDS file with the most updated version of your design, and also a file containing the size info of your design, which is needed for the final mask merging. So these files are copied into the GDS to merge folder, where all the final GDS files are in one place so that the designer in charge of the merging doesn't have to search for your files in your subfolders. So let's take a look at the example of such a regeneration script. This is the regenerate.py script. So first we have the import statement, which import your design from your DOE folder. And then this output folder, which gives names to your designs. Then we instantiate the design, of which the P cell name to be adapted with the good practices rules, such as you can add your designer name, add your key design aspects information. And finally, you will export your DOE design to a GDS and also export the layout size information. So after you run this regenerate script, the output will be placed into the GDS to merge folder, where you see the GDS files and the text files. This is all organized under the folder which is named after the user Kiara and under this GDS to merge folder. And finally, after all the DOE GDS files and layout size information files are generated, the last step is to merge all of them onto a single mask layout. So in this training material, we have put the additional script for mask merging. It's the utility to facilitate the mask merging task. So the mask merging script is actually handled by the lead designer or the mask merger of this tapeout. And the job of the other users is to follow the directions of the main designer to make the mask merging smooth, including follow the same project organization structure and follow the best practices that we have put in place among the team. It's also worth mentioning that our mask merging utility is actually based on Ruby scripting, which makes the mask merging speed quite fast. The input of this mask merging script is all the GDS files in the GDS to merge folder of each user, and also the files with size information about the designs in the GDS files, so that the lead designer or the mask merger can move designs around. And the output of this mask merging script is the single GDS file with all the merged designs. For example, here in our training material, the final merged mask will look like this, which is a hierarchical cell with all the separate DOEs collected from all the designers within the team. So now it's up to you. After you have taken a look at the example project structure we have put into this training material, you could do an exercise on your own. Extend this design project with your own name. So currently we have designer Kiara, Pierre, Jiejing, and Ruping in this design project, and you could extend this design project with your own name. So first, take a look at this topical training design project management folder and create the project structure in My Tapeout with your own name, with your own DOE designs. Then, of course, you will need to prepare for the regeneration files just to make a copy of this file from the other designers and adapt it to your own information. Then don't forget to regenerate all the designs, including your own design and the DOE designs from the other designers, including Kiara. And then prepare for your merge file to move around the GDS files from your colleagues as well as from yours. And finally, merge your designs. So hopefully that will be helpful for your large design organization. And I'm sure in time you will develop your own method of organizing the design structures among your own team.